Hi everyone, welcome to the third video of the video series Learning for some Computer Networks module. I am Lakisuru Semasinghe from SLIIT FOSS community. Without any more chit chat, let's move into the lesson. And today's lesson is about IP addressing. This is the second unit of the Computer Networks module, and in this one, you will be basically learning about IP version 4 addressing and related stuff. So, as I told earlier, this whole lesson is about addressing, and basically there are multiple types of addresses other than IP address. So we have MAC address, and then we have IP address, then we have port number. So when we take these two, IP address and port number, as a single attribute, we can call it as socket address. So I will be talking about that in next slide. And before going to that, let me explain what's the difference about these three types of addresses. So basically, we can divide these types of addresses into two types as physical addresses and logical addresses. Physical addresses, in the sense, they are bound to the hardware, like in physical manner. So it's like, let's take MAC address. It's a physical address, so it is hard coded to the hardware, such as network interface card. Maybe it could be a Wi-Fi adapter or a Ethernet card, something like that. But it is physically bind to the hardware using firmware. But when it comes to logical addresses, they are bind to the device using software. Actually, we can change that by we can easily change that, but when it is a physical address, we can't change it that easy. So that's the main difference between physical addresses and logical addresses. Physical address. Okay, before talking about IP addresses, let's talk about what are the available addresses in networking. So we have MAC address, IP address, we have port number, but port number is actually also address when it takes alongside with the IP address, and we call it as socket address. So basically, socket address is the combination of IP address and port number. I'll talk about that in the next slide. And before moving on to the next slide, let's talk about the differences between these addresses. So basically, if you talk about the major addresses, that's MAC address and IP address. So MAC address is the physical address and IP address is the logical address. So if you talk about physical addresses are bound to the device by hardware. It's like it may be hard coded to hardware as firmware. That's how we find MAC addresses on network interface cards. In Wi-Fi adapters and Ethernet cards, the MAC address of those cards are bound to those devices using firmware, and it is done by the manufacturer. So we can't change it after purchasing. Just like illegal ways to change that, but basically we take it as immutable. So when it comes to logical addresses, the address is assigned according to situation by software while we are using it. So it's like the IP address, and it is assigned to us using DHCP, and in that case, the device will be configured to that IP address according to the situation. So that in the sense, it is mutable. So that means each time we are connecting to the network, either we can change the IP address or DHCP will do it automatically. So every time we connect, there's a possibility to change the IP address according to the configuration. So that's the main difference. And when it comes to port number is used to identify the process which is running on our computer. So when you are using a network, the process is addressed to the network using the socket address. So in socket address instance, IP address with combined to port number, and in that case, IP address denotes our computer and port number denotes the process that is running inside our computer. So in that case, if we have the socket address of any process, we can just find the relevant computer and the process inside that computer. So MAC address is something different. Like it can identify the computer just as IP address, but it's not available. It's not possible to identify the computer within the whole internet. Like we can't find where this computer is, but because the MAC address is assigned by the manufacturer, so the device manufactured by that manufacturer could be anywhere in the world. But in IP address is assigned by the DHCP server or the person who are who is using it. So in that case, they will assign the IP address according to the network that the device is connected to. So therefore, the IP address of that specific device is specific to that network it is connected to. So in that case, we can find that relevant device using that IP address in a connected set of networks. So that's why the MAC address and IP address has two different roles. So let's move to the next slide. So here we can see how the software address is made. It's the combination of IP address and port number. So to divide the IP address and port number in the notation, we are using a colon. So here you can see the difference of these types of addresses. So we have MAC address, IP address, and port number. So MAC address is used to identify the computer physically within a network, and IP address is used to identify the computer logically. In that case, as I told you earlier in that slide, MAC address is bound to that device physically, while IP address is logically bound to that device, and it can be mutated according to the situation. Port number is used to identify the port in each computer. So port numbers are ranged between 0 to 65,000 and 5,535, and we'll be learning that in the next lesson, probably in transport layer. So MAC address is assigned to that device by the manufacturer of that device, and IP address is dependent on the protocol, and it is assigned according to the network, like maybe the user can define it, or the DHCP protocol will be defining the IP address of that device. So in that case, according to the network we are connected to, IP address may change. And when it comes to MAC address, each manufacturer has its own range of addresses. So let's take there are two manufacturers as A and B. So A has a set of range of MAC addresses to assign to its manufacturing devices, and for the manufacturer B, it has another set of MAC addresses to be assigned to its devices. So this MAC address is specified in the NIC or network interface part. And when it comes to IP address and port number, it is specified in the configuration file. So, and MAC address is operated in data link layer, which is known as layer 2 in the OSI ISO model, and IP address is defined in operates in network layer, which is the layer 3, and port number is operates in transport layer. So that's how these different types of addresses work in this networking. Let's start with this presentation. This presentation is about IP addressing, but actually right now we are studying about IP addressing. Even though this presentation is about IP addressing, actually now we are starting learning about IP addressing. So let's see what is an IP address. So according to Wikipedia, an Internet Protocol address is a numerical label that is connected to computer network that uses the Internet Protocol for communication. So that's the basic definition of an IP address. So basically it's a numerical label. According to the scenario, we are using different kind of representations. In computers, we are using binary, and in human use, like when we are writing, we use the decimal notation. So we are using IP address for two main tasks. First one is network interface identification. So in that, if I define it further, means when you are connecting a device to a network, each those the network interfaces get the ID. That ID is known as IP address, and it's in this case that interface gets two IDs actually. One is the MAC address and another one is IP address. So this IP address is the logical identification and MAC address is the physical identification, as I stated earlier in that slide. So the next task is location addressing. This is why IP address is more important. So in this case, as I told earlier, if there are multiple networks connected to each other, and according to these protocols, each network has its own network address, and its IP addresses belongs to that network are under that network address. So in that manner, we can easily identify the location of any IP address, and that's why we need IP addresses to address the location. So let's see. Okay, we have IP address versions here. There are two IP address versions, as IP version 4 and IP version 6, and IP version 6 is also known as IP of next generation. So in this case, earlier we only had IP version 4, and now we are using both IP version 4 and 6, and 6 is basically created for the high number of devices that will be going to connect in the next few decades, and even now we are using IP version 4 to address this issue of multiple millions of devices connected to the network. So the reason behind that is this IP version 4 has only 32 bits, and in that case, each bit can only have a variation of 2. So therefore, there could be only 2 to the power of 32 variations of addresses. So, but with this high network demand, there will be plenty of devices, like billions of devices in the future. Not actually, even now we have plenty of devices, like billions of devices. And by the time we are using only the IP version 4, there was a huge demand for IP addresses. So to address that demand, the scientists had to come up with a new version of addressing as IP version 6, and they are using 1 to 8 bits. So there will be 2 to the power of 1 to 8 bits of addresses, and that will be plenty of addresses. And even now we only have a fraction of devices to use their address. So we can use these IP version 6 for a number of decades to come. So that's the main reason we came up with IP version 6. And it's also the reason to call it as IP version of Internet Protocol of next generation. So these IP version 4 addresses are represented as a set of 4 numbers. Let me show you. So IP version 4 address will look like this. So there will be 4 numbers separated by a dot. So this number could in the range of 0 to 255, and all these numbers will be within that range. When it comes to IP version 6, there will be a group. It is represented as 8 groups of 4 hexadecimal digits. So like this, you can see there will be 8 groups with 4 hexadecimal digits, but there are some tricks to simplify this. In that cases, we can eliminate some numbers according to some defined rules. So in that case, we can make these numbers shorter. So these are separated by colons and usually have 4 hexadecimal digits for each 8 of these groups. So that's it about IP address versions. And next slide. Okay, we have IP address types. There are 2 types of IP addresses according to their public and private domains. So public addresses are used to address any device or any host over public networks such as internet. But when it comes to private networks, it is only accessible within that private network. So we can have multiple private networks using the same range of IP addresses. So these 2 types of addresses are completely separated. So with the public address, you can't communicate with the private address, and that's the basic rule of these 2 types of addresses. So when you are using a private network, you will be definitely getting a private address. As an example for private networks, mostly our home networks are private networks, and internet is a public network. So you know there will be a router between our home network and private network, home network and public network such as internet. So the networking addresses using in the internet is different from the networking addresses we are using here in our private network. So as I told earlier, we can communicate between public address and private address. So in that case, the router will use a mechanism called network address translation, or as an abbreviation NAT or NAT, to address that issue. So when communication happens between these 2, public address and private address, then network address translation will happen and do that job. So these public addresses are assigned to, as I told you, there is a router. So our ISP assigns a IP address, public IP address to our router, and our router assigns a private IP address to our device. If I tell you it again, the ISP will assign our router a public address, public IP address, and our router will assign our devices, all of our devices connected within our private network. Those devices will be get a private IP address by our router, and that's how it works. And the router will do the network address translation between these two types of addresses. So this public addresses are belongs to IANA, and this IANA will do this distribution of IP addresses to each ISP in each country and each region in that set of according to set of roles. And also there is these private IP address ranges are also defined by IANA, and these reserved only for this private IP, private addressing, private network addressing. So you can see what are the private network address ranges reserved by the IANA. And for some additional knowledge, I think all of you know that North Korea is like it is isolated from rest of the world because of multiple reasons. So, but most probably you don't get to know much about North Korea, and it's same also within North Korea. North Koreans don't get the chance to get much more information from outside the world. So this is because North Korea has a small set of computers connected to the network, not like any other country. It's a very few number of computers, and those computers are connected using a private network. It's not like the public network we have in Sri Lanka or any other country. So in that case, that private network is using the private IP address range. So anyone can't access the internet through that private IP address. Private IP addresses, because there's no network address translation between that private IP range and public IP. So any network activity within the North Korean computer networks, that data don't reach the public address. Interconnection of public and private network. Let's think this is the internet and this is the home network. So without the router with NAT, you can't communicate between these two networks. And this is the same logic used by North Korean government to prevent their citizens accessing the internet. Let me explain it further. So just think it's your home network and you don't have a NAT enabled router. So you can't talk to the computers in the internet or any network connected to the internet other than our own network. So just like that, the North Korea has a small number of computers connected to the network, which is an intranetwork. So within that intranet, the computers are connected using private IP address. So as I told earlier, if the computers are connected using private IP addresses, they can't talk to the computers with public IP addresses or any network connected to the public IP addresses without using this NAT. So as North Korea government doesn't have a NAT installed to their public intranet, the citizens of the North Korea can't access the information in the external servers or anything else outside North Korea. So that's why the North Korean network is so much isolated from the world's public internet. That's how North Korean government prevent the other countries accessing North Korean computers as well as North Korean computers accessing external websites. Okay, let's move to the next slide. Here we can see the structure of an IP address. So IP address consists of a portion called as network ID and host ID. So this network ID is globally unique to each network if it's a private public network address. So this can be used to identify the network it belongs. So if computer is having a IP address with the network ID, let's take it as A. So all the computers in the world know this computers belongs to the A network. So host ID is unique between each network. So if we take network ID as A and host ID as B, so this means this IP address belongs to the network A, and this IP address belongs to B, computer B of network A. So that's how this structure of the IP address is developed. So even this is used in private IP address range also. So we just same as public IP address range, the network ID is used to identify which network this IP address belongs to. So there are multiple types of special IP addresses found in this according to this structure of IP address. So first we have network address. So this network address is used to identify the network among other networks. So this will make it possible to identify any net any IP address to find which network that IP address belongs to. So to make it happen, the network ID bits are kept as it is, and all the host ID bits of that IP address are changed to 0. So that's how a network address of any network is formed. So when it comes to limited broadcast address, it is used to send broadcast messages within that same network. That means the local network. So in that case, all the network ID bits are turned to 0 and all host ID bits are turned to 1. So then we have direct broadcast address. So this is used to send broadcast messages to external network. So in this case, all the network ID bits are kept as it is and all the host ID bits are turned to 1. Then we have localhost address. So this is, you all know what is localhost is. Localhost is the local computer we are working on. So we can also call it as this host on this network. So we are using this IP address to identify the computer we are working on. So to make it happen, we have to turn all the bits in the IP address, both network and host, to 0. So maybe you have seen it. It will be look like this: 0, 0, 0, 0. This is the local host address. So we also have an address as loopback address, which is 127.0.0.1. But these two are not the same, but kind of same. Let me explain what it is. So in this loopback address, it's not we are using that in most of the cases we don't use this local host address, which is known as this 0000, but we use this loopback address to route the traffic back to the same computer. So in this case, this IP address will route the traffic within the network interface card without letting them go to the route and come back. So that's how it is. And we have a specific custom local network. This is something similar to sending a message to a computer, but in this case we can only use this within our network. We can't use this to another network because as it defines, it's only within local network. So we use this IP address to identify a device within the same network. So in this case, all the network ID bits are turned to 0 and all the host ID bits are kept as it is. Then let's move to next slide. Okay, let's see what subnetting is. So subnetting is the task of dividing an IP network into two or multiple IP networks. So to achieve that, we have to use the subnet mask. So subnet mask is the subnet mask will be used throughout this IP addressing to define up to which number of bits the IP address is using to identify the network. So if we take there's IP version for address like this. So this is the IP version for address. So just think the first 3 octets are used to identify the network. So this if one octet is 8 bits, so there are 3, it will be 24 bits. So these 24 bits will be used to identify the network which this IP addresses belongs to. So when we're talking about subnet mask is the number which is denotes this number of bits. So in this case, it's 24 instance. We are using this using binary. So it will be we'll be assigning 1 bit for each of these network address bits. So it will be like 1, 2, 3, 4, 1, 2, 3, 4, like this. And for the first bits, we'll be using 0. So likewise, this IP address will be Okay, let's see what subnetting is. So subnetting is the activity of dividing an IP network into two or multiple IP networks using the rules. So all you know that there will be 32 bits in any IP address of IP version 4. So that consists of the network ID, which is used to identify the network which that IP address belongs to, and a set of host bits which are used to identify which is the host that IP address belongs to within that network. So an IP version 4 address will look like this, and let's assume the first three octets of this IP address is used to identify the network that this IP address belongs to. So it will be look like this. So as an octet, it has 8 bits. So altogether there will be 24 bits. So as a notation, subnet mask will be also a binary number, which is more similar to an IP address. So we have created that using the same structure as IP address, but turning all the network ID bits to 1. So if this is the IP address, all this part will be the complete set. From here to here will be 1. So there will be 24 ones here, like all these bits will be 1 and rest of these bits will be 0. So this creates the subnet mask of 255, 255, 255 and 0. This 0 comes here. And so by this is how it is denoted within the computer by in binary, but we are writing it, we can write it like in decimal, but for more easier way we are using the prefix. So in that case, if we take this IP address as an example, let's take it as 192.168.1.0. So and the subnet mask is according to that 24 bits. So we are writing the number of bits of that IP address which is used to denote the network ID of that IP address. So this is how we write it as the prefix of that network IP address. Okay, let me explain it further. So as I told in the earlier slide, we can take an IP address like this. So it will be easier. So I'll take this as the example IP address, and this is the example subject mark. So when we write it in binary as we use it within the computer, so it will be written like this. So there will be 32 bits of binary digits, and there will be a same size of subnet mask. So this is what happens within the computer. The computer will be calculating the network address using AND operation between these two numbers. So it will be do AND to this and this, and take the result and place it here. So as you can see, where the subnet mask is 1, all the IP address bits will be copied as exact, but when it comes to 0, everything will be 0. So this is how network devices calculate the network address of the IP addresses which comes to them. So in this case, the subnet mask will be 255.252 and 255.0. So it's exactly 24 bits of from the beginning. So we denote it here as 24 as it should. And that's it about subnet mask. And let's talk about classful addressing. So earlier we used classful addressing, which divides the whole network into 5 separate ranges of IP addresses. So those classes are known from A to E, and class A was used for large scale networks with plenty of amount of IP addresses, and class B is used for medium scale networks, and class C is used for small scale networks like home networks with the number of devices less than 256. But there was also another class B and class E, but those were not used for the daily assignment of IP addresses. Because the class B was used for multicasting purposes and class E was never used, but it was for usage purposes. So this classful addressing is the technique which is used to allocate the IP addresses according to a set of categories. So this divided the IP address, the structure, as I told earlier in the third or fourth slide, the structure of an IP address was network part and host part. What this classful addressing basically did was it divided the network part according to the number of IP bits into subnet masks. So class A only had 1 octet, and class B had 2 octets, and class C had 3 octets. So I'll explain that in the next slide further. So here you can see how class A had, it only had 1 octet for network ID and it had 3 octets for host ID. Class B had 2 octets for network and 2 octets for host ID. In class A, there were 3 octets for network ID and only 1 octet for host ID. So this was, and they used a special way to divide those IP ranges. So in the IP address of class A, they were begin like all zeros in the first 4 bits. In class B, it was started as 1000. Class C started as 1100. This was all about these 4 bits, the very first 4 bits of an IP version of address. So according to these rules and regulations, there were like 1 to 8 possible networks in class A, and this much of host per each of those 1 to 8 networks. So it actually class A had the largest number of hosts, while least number of possible networks. Class B had this much of networks and this much of hosts, and class C had this much of networks, a very big number of networks and a very low number of hosts. But still, for a small network like our home networks, we don't need these 254 devices or 54 IP addresses. So still, this is too much. And sometimes there will be networks which don't need this much of like 65,000 of IP addresses, but they still need more than 254 IP addresses, like maybe 300, 400, 500, like that. So because of that, they don't have to use class A obviously, but they can't go with class C either. So because they need 500 addresses, but 254 won't suit them. So they had to use 65,000, this much of IP addresses in class B. So that was a very waste. So that's why they had to find another new technique, and that is classless addressing. So this is the successor of classless addressing, and this enables the ability to create subnets with flexible number of IP addresses. Like it is not 100% flexible, but it's way more flexible than classful addressing. So this has 2 variants: as fixed length subnet masking, variable length subnet masking, and these are the 2 techniques used to make those 2 variants. So let's see what is fixed length subnet masking. In short, we call it as FLSM. So in this case, the value of the subnet mask is constant throughout all subnetworks. So in that case, if we take 24 as the subnet mask, all the networks, all subnets in that network have 24 as a subnet mask. So all the networks. So as an example, a network with subnet mask 24 has 8 bits for host addresses. 8 host bits are there. So in that case, there will be 2 to the power of 8 IP addresses for host. So in that case, 2 to the power of 8 in sense 256. So basically, there will be 2 addresses assigned for network address and local limited broadcast address. So we can subtract those 2, and there will be still 254. Yeah, 254 IP addresses. So all of these networks will have 255 IP addresses. So any network don't need this much of, like, just think we have a home network and there will be only like 5 to 6 devices. So we don't need this much of IP addresses. We like 8 IP addresses, 8 like 6 IP addresses will be enough because we only have 4 to 5 devices. So in that case, there will be much more waste in this IP addresses. This 24 subnet mask IP addresses. So we can't use this without any waste. So we have to come up with more efficient way. That's the efficient way is the variable and subnet masking. So before going into variable and subnet masking, I'll explain this fixed length subnet masking with an example. So just think we have this IP address 192.168.1.0. This is the network address of our network. And so according to the example I talked earlier in that slide, we can have 2 to the power of 8 IP addresses within this network. Sorry, so it is a 24 bit /24 network, so it has a subnet mask of 24. So it's possible to have 2 to the power of 8 IP addresses within this network. But if I want to divide this network into 4 subnetworks, we can divide this according to the fixed length subnet masking. So in this case, the IP address we are already having is this. This is the network address, and the first 24 bits, like from here to here, are fixed because it is the network address. We can only, because the subnet mask is fixed because it's the network address. So we can't change it. But the rest of the bits, like these 8 bits, can be changed as like we like. So we are using these 8 bits to create more networks within this network. So that's what we are calling as subnetting. So if I want 4 subnets with as this is fixed length subnet masking, we can't use different size of subnets, subnet mask. So we have to use the same subnet mask in. So it will generate same size of subnets. We can't use variable sizes of subnets. So I will be needing 4 subnets within this network. So because of that, I have to divide this host portion into 4. So I'll be doing that using this method. So I'm writing this decimal number in as an octet in binary. So it will be like 0, 0, 0, 0, 0, 0, 0, 0. In that sense, there will be, according to that, there will be 8 digits to denote this first portion. That's what I'm writing. That's why I'm writing 8 0. So if we can change the values of these digits, we can generate different values. So we are using the same concept to generate 4 more network addresses by changing the values of these digits. But all of us know this is the network portion and this is the host portion. So the network portion will be always in the leftmost corner of the IP address. So we have to use the leftmost corner of this leftmost digits of this IP address for using create more networks. So subnetting is creating more networks. So we have to use the leftmost host bits to add more bits to network addresses. So that new bits we are allocating from host bits to network bits will be known as subnet bits. Subnet. So the new structure of the IP address will be network ID, net ID. Then we will be having subnet ID, subnet ID. Then only we are having host ID. All of these parts will be within that 32 digits of IP version 4 address. So let me explain how it happens. So we will be needing 4 different subnets. 4 different subnets in the sense we will be needing 4 different combinations to identify these 4 different subnets. So the as we are using binary, the easiest way to create 4 different combinations will be using 2 binary digits, and using these 2 binary digits we can come up with like this: 0 0 0 1 1 0 1 1. So this will be the 4 combinations we can have using minimum number of binary digits. So we'll be using these 2 binary digits as the subnet digits, subnet ID bits, to denote this difference between these 2 subnets, these 4 subnets. So we can generate subnet as by using 0 0. It will be like 0 0 and 6 more bits, 0 1 and 6 more bits, 1 0 and 6 more bits, and 1 1 and 6 more bits. So that's how the 4 subnetwork addresses will be created. So we all know that the binary values will go up, the value of a binary digit will go up when it goes towards most significant bit. So as this is the 8th bit of this octet, this has the value of 128. This is the 7th bit, so it has the value of 64. So we can generate as all the network addresses will have the host bits as 0. So all these will be zeros, 6 zeros, zeros and 6 zeros. So we can identify the value of these 2 with these 6 zeros. So the new addresses of the network address of the new 4 subnets will be 192.168 1 dot, then we have to calculate this. So if these 2 are zeros and all these are always zeros, so 0, and most importantly the network and subnet ID will be, subnet is also a network, so network ID and subnet ID all together there will be there was 24 network ID bits, and we have taken 2 like this, 1 and 2. So we are taking these very first 2 host bits as subnets, so there will be 2 subnets and subnet, and rest of the bits for rest of 6 bits for host ID. So as I told earlier, subnets are also networks, so it will be also taken as a network address, network ID. So 24 plus 2 will be 26. So the new subnet mask will be 26. So this is the first ever new subnet mask, subnet address we can have. So second subnet address will be starts with 0 1 as the subnet ID. So it will be also starts same as previous network, previous subnet address 1, but here 64 to the power of 7, 6, to the power of 6 will be 64. So 64. Next will be same as network ID, and here 1 0. So to the power of 7 will be 128, and to the power of 6 will be 0 here, and all of these are also 0. So 128. And last 168 1 1 instance 192 128 plus 64 will be plus zeros will be 192 26. So that's how FLSM works. So let's see how variable length subnet masking works. So the value of the subnet in variable length subnet masking, value of the subnet mask can be changed. So there could be subnet mask with 10 subnet bits and like 10 host bits, 20 host bits, anything between 1 to 32. So that's why this known as variable length subnet mask. The subnet length of the subnet mask will be vary according to requirement. So this is used to address the case of different size subnets. So this allows the users to create different size subnets within the same network. Okay, so let's see how this works. So I think okay, let me take the same IP address as earlier for the network. So 192.168.1.0 and subnet mask will be 24. So just think, in this case, I have requirement for 4 subnets, but one subnet needs to have okay, let's take 4 subnet as A, B, C, D, and the subnet needs let's say okay, 1 to 8 addresses. This needs 64. Okay, so this needs 32 and this needs 16. So first you have to identify how many addresses there are in this requirement. So you can easily see it is less than 256. So in that case, we have to identify how many addresses exactly we need. So there will be as it is less than 256. We know to create 256 addresses we need 8 bits. So it's less than 256. We can easily create it within this network because we have the subnet mask is 24, so that means 8 bits are remaining for host IDs. So 8 bits remaining for host IDs, in the sense we can create up to 256 addresses, but here the requirement is less than 256, so it is possible to create it within this network. So then we have to identify how many addresses are required. So here if we calculate okay, let me take the calculator. Okay, so 128 plus 64 plus 32 plus 60. Okay, 240. So this is the number of IP addresses we require. So to make this happen in FLSM, we can't really do that because all the networks should be equal in sizes, or otherwise there will be a problem. So, but as VLSM address this issue, we will be able to create this required network. So first, we have to identify how many bits are required to create a network with 1 to 8 addresses. Actually, we can get this in the equation of this equation. So 1 to 8 equals 2 to the power of x. So if we find x, we can find how many bits are required to create this subnet. So that will be this x. This stands for the number of first bits in that subnet. So we all know that 2 to the power 8 is 2 to the power 7. So x equals 7. So that in sense we need 7 bits for host. So as you can see, there are 24 network bits. So that in sense there will be 8 host bits available for us to make changes and modifications. From those 8 host bits, we have to take 7 for creating this network subnet A. So we are taking this 7. You all know the rightmost bits of an IP address will be used for host bits, and leftmost are used for network bits. So therefore, this will be for subnet ID. So we are putting the least number available here. We can put that we available to put here. So it will be 0. So we have put in 0 and allocating this for the allocating 0 for all these to create network A. So this makes 192.168.1.0 IP address for network A, and this comes with to the power of, so it also already have 24 bits for network address, and here it comes with one subnet address, subnet ID. So 24 network ID bits with one subnet ID, it will be 25. This will be for network A. So now we can see all the combinations of this network is taken, except we have to change this 0 to 1, and we can do this. All these combinations are already taken with the 0 in front, so we have to change the front digit to 1. So now we have seven vacant combinations, to the power 7 vacant combinations with 1 in the front. So now see, let's see the second network. It's network B, and it needs 64 addresses. 64 addresses in the sense, if we apply the same equation, we'll be needing 6 host bits. So we are allocating these 6 host bits and keeping this for network, but we can't keep this empty, so we have to use the least available number. So least available number is 0 here, because this is never used. This combination 1-0 combination is never used. 0-0 combination has been used in earlier, but the number 0 was the only number used for the first digit in the previous subnet, but here we are using 1, so we can use 1-0 combination. So in this 1-0 combination, we can have 6 more combinations for the host bits. So all this will be zeros. So in that case, network we will be having 192.168.1 dot. So this is the first number. So this is 2 to the power of 7. So that means 128, and this address have 2 subnet digits. So that means 24 plus 2, 26. So I'm also, I'll create the next subnet also. So in that case, we have used 1-0 combination. Without going further into another third, without going further, let's create another 64. So, okay. I'm creating another 64. So I can show another thing by another trick here. So let's take this as 664, another 64. So now altogether there will be 256 addresses. So it's still possible, right? 256 is to the power of 8, so there's 8 bits, but it's still possible for 64. So here this combination is already used, and 0 blah blah blah, this combination is already used. So the next available combination with highest number of bits will be 1 1. So we will be using this combination to create the next subnet. So it will be 1 1 and 6 vacant digits. Using this, so this will be 2 to the power of 7, and this will be 2 to the power of 6. So 128 is equal to 128, and this is equal to 64. Yeah. It's 64. So 128 plus 64 will be 192. So the next type address, network C, will be 192.168.1.192, and here also we will be using 2 for subnetwork IDs. So 24 passes to 26. That's how a VLSM will be used to address this variable length, variable size of subnetworks within the same network. So that's it for today's video. Thank you very much for joining. See you in the next video.